Sorry. Just having a bit of trouble with the Zoom not wanting to start. So we're going to start off with an arc length problem. We turn on my video. I have to change one second. Hopefully you can see the arc length problem. There we go. Maybe. There we go. Finally, hello, welcome. So starting off with an arc length problem, then we're going to talk about some trig sub and some partial fractions. So here's the setup. Find the length of the curve y equals the natural log of secant of x on the interval from pi over 6 to pi over 4. So length, or they could have said arc length, but when we read a question like this, we are reading the fact that we have to use the arc length setup. So very generically, if you're finding the arc length, we're always going to get L equal to the integral of ds. That's it. Now, we're going to do more with that, but that's always the starting place. And just as kind of a quick aside, if it was surface area, it'd be the integral of 2 pi r times ds. Okay, so here, just like every time, we're going to get the integral of the square root of 1 plus the derivative of our function squared. Whichever way it makes sense to take the derivative. If y is a function of x, it's dy dx. If x is a function of y, it's dx dy. And then we're going to go from x equals pi over 6 to x equals pi over 4. Let's see. So the derivative of the natural log of secant of x is 1 over secant times secant tangent, which just becomes tangent. So here our dy dx is 1 over the stuff times the derivative of the stuff, but that just simplifies to being tangent. So here we're going to get the integral from pi over 6 to pi over 4 of the square root of 1 plus tangent x quantity squared. 1 plus tangent squared. Do we know a trig identity for that? We certainly do. It's my favorite one. I've said it a few times. Have I said it in here? Okay. Yeah, you know what happens when you tan? I tan and get sexy. So this is going to be the integral from pi over, I don't actually tan, I burn, but whatever. The integral of the square root of 1 plus tangent squared becomes secant squared x. How convenient is that? The square root of secant squared is just secant. I should actually say the square root of secant squared is actually the absolute value of secant, just like the square root of x squared is the absolute value of x. But here, since we're in the first quadrant between pi over 6 and pi over 4, we know that all trig functions have positive values. So we're just going to say it's secant, not the absolute value of secant. So we're going to get the integral from pi over 6 to pi over 4 of secant of x. And then, since we've already talked about trig integrals a little bit, we might as well say, how do you find the integral of secant? Good question. Well, there's a trick. The integral of secant of x is one you should just memorize. But here's the trick for finding it. You multiply the top and bottom by something kind of unwieldy. I'm going to multiply secant x over 1 by secant x plus tangent x over secant x plus tangent x. Which you might ask, how did someone come up with that? They really did the problem a totally different way and then eventually found the answer and said, oh, there's this other shortcut I can take. But really, there's a totally different method of doing this integral that requires some other methods we haven't talked about yet. Multiplying off the top, I get secant times secant plus secant times tangent. Over secant x plus tangent x. Now check out this slick u substitution. If we let u equal the denominator, u equal to secant of x plus tangent of x, our du, the derivative of secant, is tangent squared, the derivative of tangent is secant x times tangent x. Oh, look. My du is, oops, I made a mistake. I made a huge mistake. Wow. Wow. Holy wow. Oh my God. Shame upon my family. Terrible. You guys let me get away with murder over here. What's the derivative of secant? You guys tell me. Silly, I don't know. Thank you. Yes, correctly. Secant x times tangent of x. And what's the derivative of tangent of x? Yes. Okay. Phew. Getting carried away over here. But look, now that we've done it correctly, the du is exactly the numerator. It is exactly secant squared x plus secant x tangent x all times dx. So we can rewrite this integral as the integral of du over u, whose antiderivative is the natural log of the absolute value of u. So we end up getting that the integral of secant x is equal to the natural log of the absolute value of secant of x plus tangent of x. And that is one you are going to want to memorize. So write down here again, the integral of secant of x is equal to the natural log of the absolute value of secant of x plus tangent of x plus c. So back to the problem at hand. That means our integral from pi over 6 to pi over 4 of secant of x dx is going to be the natural log of the absolute value of secant of x plus tangent of x evaluated from pi over 6 to pi over 4. Which then is going to be the natural log of secant of pi over 4 plus tangent of pi over 4 minus the natural log of secant of pi over 6 plus tangent of pi over 6. And I do think it's fair to expect us to simplify this. Secant I never know. I know what cosine is, which secant is the reciprocal of. Cosine of pi over 4 is root 2 over 2. So secant of pi over 4 is 2 over root 2, which reduces just to the square root of 2. The natural log of the square root of 2 plus tangent of pi over 4 is 1. Tangent. Cosine of pi over 6 is root 3 over 2. So natural log of pi over 6 is 2 over root 3. And tangent of pi over 6 is 1 over root 3. And I wouldn't do any more simplifying after that. I would leave it like that because I don't want to do it. That's enough. So there's a cool arc-length problem with some trig stuff inserted in the middle there. Yeah. So I know I said trig substitution, but I forgot that we still had some other trig integrals we had to talk about. Yeah, let's do that. So last class, we had just briefly talked about the integrals of a power of tangent times the power of secant. I want to do one more like that just to remind you what we're doing, and then we'll look at a couple other just very straightforward. We'll finish off the list of integrals of all the regular basic trig functions. So let's look at one more tangent secant example, if I can remember. Yeah, sure. Let's say we want to do the integral of, I don't remember what we did last time. Well, let's say we have secant to the 4th x times tangent to the 6th x dx. Whenever you see powers of trig functions like this, most of the time, there are some exceptions, most of the time you're letting u equal either secant or tangent, or whatever your functions are raised to powers. I actually don't know what the right choice is here. I'm just going to think about the right choice. So I can either let u equal secant of x or u equal tangent of x. If I let u equal secant, my du would be secant times tangent, which would soak up one of the tangents, leaving my not u choice raised to an odd power. And that is not what I'm looking for. I don't want to do that because my non-u choice would have an odd power left over. That is bad news. So instead I'm going to let u equal tangent. My du, my derivative, is going to be secant squared x dx. And then when I soak up a secant squared, I'm still left with an even power of my non-u choice, which is what I'm always looking for. I'm trying to do powers of trig functions. So I'm going to rewrite this as the integral of secant squared x times tangent to the 6th x times secant squared x dx. And then we're going to replace stuff. My secant squared x dx is equal to du. My tangent to the 6th is equal to u to the 6th. And for secant squared, the leftover secant squared, we're going to use the trig identity. We're going to say that 1 plus tangent squared x is equal to secant squared x, but tangent is really equal to u. So 1 plus u squared is equal to secant squared x. So we can replace the secant squared here with 1 plus u squared. And then we can rewrite this as the integral of 1 plus u squared times u to the 6th times du. We can distribute the u to the 6th to get the integral of u to the 6th plus u to the 8th. We can differentiate. We get u to the 7th over 7 plus u to the 9th over 9 plus c. And then we plug in our trig function u equal to tangent, and we get tangent to the 7th x over 7 plus tangent to the 9th x over 9 plus c. For powers of secants and tangents, or cosecants and cotangents, you can always do a u sub except for one case. So the one case where a u sub won't work is if you have secant raised to an odd power and tangent raised to an even power. So for example, the integral of secant x times tangent squared x dx, you cannot do a u sub. Or the integral of secant cubed x dx, you cannot do a u sub. And I guess since I brought it up, we should do it. But it's kind of gross. It's actually not that gross. It just feels a little bit tedious. So let's do one of these. Yeah, let's do secant cubed. So here's how you would integrate something where you had an odd power of secant and an even power of tangent. Do I have an even power of tangent here? Kind of, actually I do. How many tangents do I have? This many. Is that an even number? Is 0 even? It definitely is. 0 is 100% even. What's the definition of being even? Divisible by 2. Is 0 divisible by 2? 1000% divisible by 2. Or you can just say, right, even and odd numbers alternate. 5's odd, 4's even, 3's odd, 2's even, 1's odd, 0's even, -1's odd, -2's even, -3's odd, -4's even. It totally 0 is definitely an even number. It's definitely not an odd number. So we definitely do have an odd power of tangent. I'll point out, you can also apply this logic when trying to integrate something like sine cubed x dx. I would definitely do a u sub here. We might come back to this. You would definitely let u equal cosine. We'll come back to that one. But here, for the integral secant cubed, you have two things you have to do, and you can do them in either order. You're going to use a trig identity to rewrite it, and you're also going to do integration by parts. And I usually prefer to start with the integration by parts, although either way is fine. So I'm going to rewrite this as the integral of secant x times secant squared x dx. Because then there's a more obvious choice for what our dv should be. dv should be something that's easy to anti-differentiate. And secant squared definitely is, because I remember that the derivative tangent is actually secant squared. Sorry about the mistake earlier. I feel bad about it. I was like, I should know my derivative tangent is secant, but okay. So this is going to be my choice for dv, and this is going to be my choice for u. So u is equal to secant of x. My du is going to be secant x tangent x dx. My dv is going to be secant squared x dx. And my antiderivative secant squared is tangent of x. And then we're going to rewrite this. We're going to get u times v secant x times tangent x minus the integral of v du secant x times tangent x. Well, really, secant times tangent is secant x times tangent squared x times dx. And now is when the trig identity comes into play. We're going to replace tangent squared with, well, 1 plus tangent squared x equals secant squared x. So tangent squared x equals secant squared x minus 1. So we're going to replace that with secant squared x minus 1. And we're going to rewrite this as the secant x times tangent x minus the integral of secant x times secant squared x minus 1. We're going to distribute that secant x to get secant x tangent x minus the integral of secant cubed x minus secant x. And then we're going to break up this right side so that we have secant x tangent x minus the integral of secant cubed x. And minus a minus makes plus the integral of secant x. Hey, check that out. The thing we were trying to integrate showed up again. We've seen that happen before with the e to the x sine of x, with the e to the x cosine of x. So look, we have the integral of secant cubed x dx equal to secant x tangent x minus the integral of secant cubed x dx plus the integral of secant x, which we just found out was the natural log of the absolute value of secant x plus tangent x. It's a lot of secants and tangents. So then we're going to add the integral of secant cubed x to both sides. And we're going to get 2 times the integral of secant cubed x equal to secant x tangent x plus the integral of secant, which is the natural log of the absolute value of secant x plus tangent x. And then to finish off the problem, we multiply both sides by 1/2 or divide both sides by 2. And we get that the integral of secant cubed x dx is equal to 1/2 times secant x tangent x plus the natural log of the absolute value of secant x plus tangent x. Oof, plus c. Sorry, I got a little cramp there. And every time I taught the second quarter of calculus or the second semester of calculus, I would always ask this question on the test every time. I would tell students I was going to ask them this question. I think this is a good question. It makes people think. You have to use integration by parts and a trig identity. So it wouldn't surprise me if either one of your instructors asked this question on a test. It also wouldn't surprise me if they didn't. I know it's not super helpful, but it's the truth. So let's finish off talking about trig integrals, which is totally different than trig substitution, by recapping the integrals of the 6 basic trig functions, a few of which we know already. The antiderivative, or the integral of cosine of x, is equal to sine of x, which I normally wouldn't start with cosine. I would normally start with sine. Sorry about that. Let's write sine above that. The integral of sine of x is equal to negative cosine of x. And then we have tangent and cotangent, which have similar antiderivatives. So for the integral of tangent, have you guys seen this one yet? Integral of tangent? I mean, you probably have at some point just without even knowing it, because someone might have asked you the integral of sine x over cosine x, which we could definitely do a u sub for. We let u equal cosine. Du is negative sine dx. So negative du is equal to sine x dx. And we can rewrite this as the integral of negative du over u, which is equal to the negative natural log of the absolute value of u plus c, which is the negative natural log of the absolute value of cosine of x plus c. That's one way of writing the answer. Or the -1 coefficient comes up as the power of cosine, and cosine of x to the -1 power is the same as the reciprocal of cosine, which is secant. So we write this also as the natural log of the absolute value of secant of x plus c, which shouldn't be surprising considering we started class off by talking about finding the arc length of the natural log of secant, When we took the derivative of the natural log of secant, we ended up getting tangent because it was 1 over secant times secant tangent. So the integral of tangent of x dx is equal to the natural log of the absolute value of secant of x plus c. Or negative natural log. Really, both ways of writing it are perfectly acceptable. People go back and forth between them. On the other hand, the integral of cotangent of x, we can make the same sort of u substitution. It's going to be the integral of cosine x over sine of x. We would let u equal sine. Our du is exactly cosine x dx. And so this becomes the integral of du over u, which is the natural log of the absolute value of u plus c, which is the natural log of the absolute value of sine of x plus c. And nobody writes it a different way. You could, if you really, really wanted to, write this as the negative natural log of the absolute value of cosecant of x plus c, but no one ever writes it that way. I don't know why. It just feels, we don't. All right, that's 4 down, 2 to go. Well, actually 1 to go, because we already know the integral of secant. The antiderivative of secant of x dx is the natural log of the absolute value of secant of x plus tangent of x. Let's see. I don't know why I'm boxing this one versus the other ones, but I just did. I guess I'll write this one over here. Not important. Well, that's not true. It is important, actually. It is important that the integral of secant of x actually comes up in a lot of, well, maybe not a lot, in one place I'm familiar with, which is, so you know how when people like make maps, it's not like a 1-to-1 scale, right? Like you go further out to the edges, things like Greenland looks super huge. It's not really super huge. It's because most of the maps we use a Mercator projection, or like projecting the globe onto a flat surface. And the amount that we're off by ends up having to do with finding the integral of secant of the angle that we are from like the equator. And finding this integral actually was a very challenging thing to do once upon a time. And later on, if you're interested, we can talk about how you find it, and you have to use like partial fractions and some other kind of cool trick stuff. But that's not what we're talking about. I'll just say, if you want to talk about that sometime, come see me in office hours. I think it's really neat, but obviously it's not that important as far as you for this class, but definitely important for maps. So the last one is the integral of cosecant of x. Cosecant, I always want to write cosecant wrong. Let's just write it again. Which actually turns out to be very similar to the integral of secant. This shouldn't surprise you, right? All of your derivatives, sine and cosine, secant and cosecant, tangent and cotangent, have similar patterns. In the same way, the integrals also have similar patterns. Each pair of co-functions kind of has the same derivative or antiderivative up to a co-function. So cosine and sine, same. Secant and cosecant, same. Tangent and cotangent, same. Right? You look back here, the integral of tangent and cotangent are pretty much the same. The integral of tangent is the negative natural log of cosine. The integral of cotangent is the natural log of cosine, just sine. They're virtually the same. So we'd expect the integral of cosecant to be something like the natural log of cosecant plus cotangent instead of secant plus tangent. And it is. It's actually the negative natural log of the absolute value of cosecant of x plus cotangent of x. Or, unfortunately, and equivalently, the positive natural log of cosecant of x minus cotangent of x. Let's see. Those are the same. It's kind of weird. I would imagine one of you at least might like to know why they're the same or how they're the same. Well, let's look at this first one. If you look at the negative natural log of, you don't need to write this down, by the way. I mean, you certainly can, but it is not required. You don't have to show this. But if we bring this negative one up as the power, this is equal to the natural log of cosecant of x plus cotangent of x to the negative 1 power. Something to the negative one is just its own reciprocal, but it's the reciprocal of the entire thing. This is really the same as the natural log of 1 over cosecant of x plus cotangent of x. Okay, we're going to rewrite cosecant and cotangent in terms of sines and cosines. That's going to be the natural log of 1 over sine plus cosine over sine. Oh, great, they both have the same denominator. So we can really write this as the natural log of 1 over 1 plus cosine over sine. Let's flip the multiply. So that's really the same as the natural log of sine x over 1 plus cosine x. We're going to multiply the top and bottom by the conjugate of 1 plus cosine. That's something we often do, because the conjugate, when you multiply 1 plus cosine by 1 minus cosine, you end up with a trig identity. So now we've got on top sine of x minus sine of x times cosine of x. I probably didn't need to multiply that out. I really didn't need to multiply that out. I'm sorry. I'll unmultiply it out in the next step. On the bottom, I have 1 minus cosine squared x. 1 minus cosine squared is sine squared. And that's why I didn't need to multiply the sign on the top, because if I factor it back out, it's going to cancel with one of those signs. So the sign here cancels with the sign there. And now we've got the natural log of 1 over sine minus cosine over sine, which, hey, is exactly the natural log of cosecant of x minus cotangent of x. And that's how you show that the negative natural log of cosecant plus cotangent is equal to the positive natural log of cosecant minus cotangent. It feels like they shouldn't be the same, because you're just like, it feels like you're changing the sign, you're changing that sign, but really there's a lot of work that goes into seeing they're actually the same. At the end of the day, nobody really cares which one you use. My personal preference is to kind of keep the pattern going, meaning I like to think of the integral of tangent as the negative natural log of cosine, and the integral of cotangent as the positive natural log of sine, so that I can make the same sort of connection. The integral of secant is the positive natural log of secant plus tangent, so the integral of cosecant had better be the negative natural log of cosecant plus cotangent. So just changing sign in front and the functions to their cofunctions. That's the way I'm kind of thinking about it. All right. And that's not everything there is to say about trig integrals, but most of what there is to say about trig integrals. Yeah. Cool. So let's talk about trig substitution, which is totally different. Has, at least the integrals start off having nothing to do with trigonometry. So let's look into these. Let's say that I want to find the integral. Oh yeah, let's do this one. Let's do the integral from, sure, we'll make it not too terrible to start off with. 0 to 1 of the square root of 1 minus x squared. Well, in fact, I'm not going to do a trig sub here. I don't have to, because we know what that shape is. That shape, y equal to the square root of 1 minus x squared, is the top quarter, in this case, of a circle. Right? If I'm graphing y equal to the square root of 1 minus x squared, it's just a circle of radius 1. And I'm getting this area right here. So that integral is going to be 1/4 of pi times 1 squared, which is just pi over 4. But what if instead I said, what if I said instead I wanted to find the integral from 0 to 1/2 of the square root of 1 minus x squared? Then you couldn't just say it's some fraction of a circle, because it's not easy to see what fraction. It's not really, really not easy to see. There is a way to do this using trigonometry, but we're going to do it using trig substitution. So the idea with trig substitution is kind of like, it's almost like a backwards u substitution. Like instead of saying u is equal to some stuff in the integral, we're going to say that x is equal to a trig function that's going to give us a trig identity. So here, we're going to pick x equal to either sine of theta, tangent of theta, or secant of theta, whichever one gives us a trig identity. Specifically here, we're going to let x equal sine of theta. And the reason we're picking sine is because 1 minus x squared will become 1 minus sine squared, and 1 minus sine squared theta is equal to cosine squared theta. So here's a, oh, and then, but if we're doing a substitution, oh, by the way, I really should point out, when you let x equal one of these trig functions, you have to use a different variable. You cannot write x equals sine of x. You have to write x equals sine of any other variable you want. I would usually pick theta because trig functions. And then if we're rewriting this integral like a u sub, we have to replace dx with something with d theta. So x being sine theta means that dx is going to equal cosine theta times d theta. So we're going to rewrite this integral as the integral of the square root of 1 minus sine squared theta times dx, which is cosine theta d theta. I know most of the time for definite integrals, I say I like changing the limits of integration. Here I could kind of go either way. I'm going to change it because, well, we're going to not change it in the next one. So you'll see kind of why not changing them is good. So, but these are my x values. So if x equals 0, that means sine of theta equals 0, which means the angle theta is 0 because sine of 0 is 0. And if x equals 1/2, that means sine of theta equals 1/2, which means theta equals pi over 6. Sine of pi over 4 is root 2 over 2. Sine of pi over 6 is 1/2. Sine of pi over 3 is root 3 over 2. So there is some trig evaluation knowledge we have to have here. So we're going to rewrite this as the integral from 0 to pi over 6. And then we can do all nice stuff. 1 minus sine squared, trig identity is cosine squared. The square root of cosine squared is cosine. So this is going to be the integral from 0 to pi over 6 of cosine theta times another cosine theta, d theta, which is the integral from 0 to pi over 6 of cosine squared theta, which is why we spent some time talking about integrating powers of sine and cosine. For cosine squared, this is when we have to use the funky trig identity. That's going to be the integral from 0 to pi over 6 of 1/2 times 1 plus cosine of 2 theta. So just as a quick reminder, we talked about it, I think last class. I'll remind everybody that when you're integrating sine squared or cosine squared, sine squared theta is equal to 1/2 times 1 minus cosine of 2 times theta. And cosine squared theta is equal to 1/2 times 1 plus cosine of 2 theta. And notably, if you add those together, you get 1. Because the cosine 2 thetas cancel out, and 1/2 plus 1/2 is 1. Which you should, because cosine squared theta plus sine squared theta should equal 1. Anyway, integrating this, we get 1/2 times theta plus sine of 2 theta divided by 2 from 0 to pi over 6. And then we plug in. We get 1/2 times pi over 6 plus sine of 2 times pi over 6 is sine of pi over 3 over 2 minus 1/2 times 0 plus 0, because sine of 0 is 0. And that's going to be sine of pi over 3 is root 3 over 2. So we get 1/2 times pi over 6 plus root 3 over 2 divided by 2 is root 3 over 4. And I would stop there. Kind of super funky. Trig substitutions usually are. So let's speak a little more general. How do you know what choices to make when you're confronted with something that might be a trig substitution? Well, the first thing I'll say is don't do a trig substitution first. Look for other things. So when it comes to trig substitution, much like partial fractions, which we'll talk about hopefully today, but maybe tomorrow or Thursday, it's what I like to refer to as a method of later resort or even last resort. You want to try other stuff first, like U substitution specifically. So for example, the integral of x over the square root of 1 minus x squared dx, you totally could do this using the same trig substitution we just did. It would totally work to let x equal sine theta. And you definitely shouldn't do it that way. You should definitely do this with a u sub by letting u equal 1 minus x squared. And so on and so on and so on. I'm not going to finish that. You all should do that on your own at some point. So don't do a trig sub when you can do a u sub instead. But then sometimes you're going to be stuck with things where you have to do a trig sub. So typically, we use a trig sub when you see a square root, although you don't technically have to have a square root, but you almost always have a square root. So trig sub is used when we see something like the square root of 1 minus x squared, or the square root of x squared minus 1, or the square root of 1 plus x squared. And here are the choices. Well, here are the things you do. If it's a 1 minus x squared, you're going to let x equal sine theta, because 1 minus sine squared theta is equal to cosine squared theta. If it's an x squared minus 1, you're going to let x equal secant of theta, because secant squared theta minus 1 is equal to tangent squared theta. And lastly, if it's 1 plus x squared, you're going to let x equal tangent theta, because 1 plus tangent squared theta is equal to secant squared theta. The way I tend to remember these, to be perfectly frank, is by remembering the derivatives of the inverse trig functions. What do I mean by that? Well, the derivative of the arc sine of x is 1 over the square root of 1 minus x squared. The derivative of the arc secant of x is 1 over absolute value of x times the square root of x squared minus 1. And the derivative of the arc tangent of x is 1 over 1 plus x squared. Look at that correspondence. The arc sine matches with the 1 minus x squared. The arc secant matches with the x squared minus 1. And the arc tangent matches with the 1 plus x squared. So that I know that when I'm thinking about the trig sub, if I see an x squared plus 1, I should be using tangent, because the derivative of arc tangent has an x squared plus 1. Or if I see an x squared minus 1, I should be using secant, because the derivative of the arc secant has an x squared minus 1. I know it's kind of a roundabout way of getting there, but to me it makes a lot of sense. And it's not a coincidence, right? These happen this way because this is the way the functions work. So let's look at some more examples. Let's say we have, I don't want to get too crazy here. Yeah, let's start with this one. Let's say we have the integral, an indefinite integral of x squared over the square root of 1 plus x squared. Sadly, not a u substitution, right? There's an extra x up there. This is definitely going to be a trig substitution. So we're going to start off by letting x equal tangent theta. The easier way to remember this is, if there's a plus sign, the plus looks like a t, and tangent starts with t. And if it's a minus sign, well, subtraction starts with s, and secant or sine. There's not a good one for them, but you have to figure it. So for tangent, my dx is going to be secant squared theta d theta. And then we're going to start plugging away. So we're going to have the integral of, so x is going to be tangent, so I have a tangent squared theta. In the denominator, I have the square root of 1 plus tangent squared theta. The whole point here is the thing inside the square root should become something that's easy to take the square root of and get rid of the square root. And then finally, vitally here, dx is secant squared theta times d theta. Oh man, I picked a real winner here. This problem is, oh man, sorry, I know where this, so here's what's going to happen in this problem. So we're going to have the integral of tangent squared theta divided by 1 plus tangent squared is secant squared, and the square root of secant squared is secant. times secant squared theta. And secant squared divided by secant is secant. And we have the integral of tangent squared theta times secant theta. It's one of those lovely situations where you have an even power of tangent and an odd power of secant. So we can make this not so terrible if we use some knowledge we already have. We already did the integral of secant cubed. So we're going to make that show up again. So check this out. We're going to let me make sure I do this the right way. I'm going to start with the integration by parts. No, I'm not. I'm going to do the trig I'm going to do the trig identity. I'm going to replace tangent squared with secant squared minus 1. It's a valid move. I'm playing chess here or something. And then if I distribute the secant, I get the integral of secant cubed theta, d theta, minus the integral of secant theta. And I am breaking them up on purpose here. D theta. And a few examples ago, we found that the integral of secant cubed theta was 1/2 times secant theta tangent theta plus the natural log of the absolute value of secant theta plus tangent theta. Minus the integral of secant, which is again the natural log of the absolute value of secant theta plus tangent theta. So then we're going to, well, we have 1/2 secant theta tangent theta. And 1/2 the natural log of secant plus tangent minus the natural log of secant plus tangent is going to be a negative 1/2 natural log of secant plus tangent. Kind of crazy. And we're not done yet. Because what variable do we start with? X. Just like with a u sub, if you do a u sub and you integrate with respect to u, then you have to change back to x. Same is true with the trig sub if it's indefinite. If you start with x, you got to end with x. So here's what we do. There's a couple ways of doing this. I'm going to show you the best way. It's not even a question. This way is the best way. So we have so far that the integral of x squared over the square root of 1 plus x squared dx is equal to, after letting x equal tangent theta, 1/2 secant theta tangent theta minus 1/2 the natural log of the absolute value of secant theta plus tangent theta. And that was by letting x equal tangent theta. I'm going to rewrite this so that tangent theta equals a fraction, x over 1. The reason I'm going to do that is because then I'm going to draw a triangle, a right triangle. And then I know that in the right triangle, tangent of theta is equal to the opposite over the adjacent. So in this triangle, the opposite side should be x, the adjacent side is 1. And the hypotenuse, we can find using the Pythagorean theorem, it's going to be the square root of 1 squared plus x squared. Or 1 plus x squared. It is not a coincidence that the missing side of this triangle is the thing that ignited this trig substitution in the first place. That's always going to happen. When you find the third side of this right triangle, it's always going to be the square root that made you do the trig sub to start off with. So this value here, well, I can look at this triangle and figure out what secant is. Secant is hypotenuse over adjacent. Tangent is opposite over adjacent. So this integral ends up equaling 1/2 times secant of theta, which is the square root of 1 plus x squared, times tangent of theta, which is x, minus 1/2 times the natural log of secant of theta, the absolute value of secant of theta, which is the square root of 1 plus x squared, plus tangent of theta, which is x, plus c. And that is typically how we go back to finding the original function, the function in terms of the original variable x. A little tricky. questions before we do a couple more examples? That's a terrible habit, but sometimes things aren't quite so nice. For example, we might have the integral of the square root of x squared minus 9 instead of 1. Let me make sure I'm not doing something really terrible again. No, it's going to be terrible again. Wow. Every time. Sorry. Let me pick a different example. Terrible. Sorry. Let's do this one. Let's do the integral of 1 over x times the square root of 9 minus x squared dx. So the idea is that we want the inside of the square root to come out to be a trig identity. Since it's a minus x squared, I know it's going to be a sine, but it's not just going to be x equal to sine of theta. If x was sine, 9 minus sine squared isn't a trig identity. So what I need 9 minus x squared to end up equaling 9 times my trig identity. I need that to be 9 minus 9 times sine squared. So that's really 9 times 1 minus sine squared, which is going to be then 9 times cosine squared. Which means I need to let x squared equal 9 sine squared, or really x equal to 3 times sine theta. I need that coefficient of 3 to make sure that the trig identity actually works out the way I need it to. So x is going to be 3 sine theta, and then dx is going to be 3 times cosine theta d theta. So then we're going to rewrite the integral. It's going to be the integral of 1 over my x is 3 times sine theta. My square root of 9 minus x squared. So you can just write in the square root of 9 minus 3 sine theta quantity squared. We've kind of done the work already, right? I literally have written here 9 minus x squared equals 9 times 1 minus sine squared. I might as well just write that if I already know that. And then my dx is 3 cosine theta, d theta. Let's cancel those 3's. And then simplifying, we get cosine theta on top, sine theta on bottom, and the square root of 9 is another 3, and the square root of 1 minus sine squared is the square root of cosine squared, which is just cosine. I will point out, for most of these problems, we ignore the fact that the square root of something squared is the absolute value of that something. Occasionally, it does come into play if you have a definite integral. Maybe we'll do an example that encompasses that, but usually we just kind of. I'm here, the cosines cancel. We bring the 3 out in front, or the 1/3 out in front, and we have 1/3 the integral of the cosecant of theta. Right? 1 over sine is cosecant. And then the integral of cosecant is going to be the negative 1/3 natural log of the absolute value of cosecant theta plus cotangent theta plus c. And then we draw the triangle again. So we take our trig substitution, we isolate the trig function. I'm going to rewrite this as x divided by 3 equal to sine of theta. And I'm going to draw a little right triangle based on that. So if sine of theta equals x over 3, which is opposite over hypotenuse, then I can draw the following triangle. The opposite side should be x, the hypotenuse side should be 3, and the adjacent side, if I use the Pythagorean theorem, is going to come out to be the square root of 9 minus x squared, the square root that started the whole thing in the first place. So then I get negative 1/3 natural log of the opposite value of cosecant of theta is 3 over x. Cotangent of theta is square root of 9 minus x squared over x. Let's see. Yeah, we got time. So let's look at, well, let's look at another one that we're gonna see actually we can get around a different way. So let's say we had the integral of x cubed over the square root of I like x squared minus 4. This is not a trig sub problem. Well, that's not true. It could be a trig sub problem. We're not going to do it as a trig sub. So if you were going to do it as a trig sub, the trig sub would be letting x equal 2 times secant of theta. So that x squared minus 4 would become 2 secant theta quantity squared minus 4, which is 4 secant squared theta minus 4. Then you factor out the 4. And secant squared theta minus 1 is tangent. Oh, no, that seems right. Yeah. Am I saying that wrong? 1 plus tangent squared equals secant. Yeah, secant squared theta minus 1 is equal to tangent squared. Yeah, sorry. But we're not going to do that. What we're going to do instead is we're going to do a u sub with a back sub. So here, if we let u equal x squared minus 4, the du is going to be 2x dx. 1/2 du is equal to x dx. And that's going to soak up one of those x's on the top. So we can rewrite this integral as the integral of x squared times x dx over the square root of x squared minus 4. The x dx is going to become 1/2 du. The x squared minus 4 and the square root down there is just going to be the square root of u. And then the leftover x squared, well, if I solve for x squared here, u plus 4 equals x squared. So that's going to be a u plus 4. And then we can divide each of those things by the square root of u to get 1/2 the integral of u divided by the square root of u is u to the 1/2. Oh, yeah, I forgot about that. Thank you, Caitlin. Yes, I totally forgot. And then 4 over the square root of u is 4u to the negative 1/2. And then if we integrate this, we get the integral of u to the 1/2 is u to the 3/2 times 2/3. The integral of u to the negative 1/2 is u to the 1/2 times 2. So we get 8u to the 1/2. Let's see. And then plugging back in that u is equal to x squared minus 4, we end up with, I'm going to distribute the 1/2 as well. 1/3 times x squared minus 4 to the 3/2 plus 4 times x squared minus 4 to the 1/2. Let's see. So it's certainly not the end all be all to all trig substitution problems, but those are some good examples. Well, I really wanted to do it. We didn't really do a secant one or a tangent one. We should do more, but I did. There was a question someone had about a integration by parts reduction formula. We should definitely go over that because it's not that terrible once we know what to do. Let me grab that. Where'd you go? Had it here. Sorry, one moment. That's actually, you know what? It's in my email. Cool. So here's the question. This is from this is like question 69 from some handout, I think. From section 8.1 or 8.2. It's asking us to show that the integral of x to the n times e to the ax, where a is a constant and n is a positive integer, is actually, I guess it doesn't have to be a positive integer. but it's equal to x to the n e to the ax divided by a minus n over a times the integral of x to the n minus 1 e to the ax dx, where a is not equal to 0. So if you're ever asked to like show a reduction formula like this is true, the idea is you're supposed to start with this and do integration by parts. So we're going to start with the integral of x to the n e to the ax times dx, and we're going to make typical choices for an integration by parts problem. We're definitely going to let u equal the x to the n part, and we're definitely going to let dv equal the rest. So if u is equal to x to the n, du is going to be n times x to the n minus 1 dx. And if dv is equal to e to the ax, where again, a is a constant, times dx, then v is the antiderivative of e to the ax, which is e to the ax divided by a. So then, if we just use the usual formula for integration by parts, it's going to be u times v, which is x to the n times e to the ax over a, minus the integral of v times du, which is e to the ax over a times n times x to the n minus 1 times dx. And then we can make just a couple adjustments to write it like that. So we can see that I can rewrite this fraction as x to the n times e to the ax over a. I can pull out the n over a here and get n over a times the integral of x to the n minus 1 times e to the ax. So showing a reduction formula is what it's supposed to be is not that terrible. It usually works out pretty nicely. You just have to make, and again, whatever integral you're starting with, you just kind of have to start with the usual sort of, I'm going to pick this for u, and this for dv, and then follow the process and try to get it to look like the thing it's supposed to look like. But they're not typically too terrible. Okay. Let's see here. There was one more arc length problem I really wanted, or not arc length, but a trig substitution problem I wanted to have you guys do. Yeah, let's do that one. Okay. Sure. Try one more. Yeah. So let's take a look at this. Let's do the integral of. Sorry, I should not just make something up. I should look at the one I actually want. Yeah, I will do that one. Okay. Let's say I want to do the integral of the square root of 25 minus x squared. Which, yes, is similar to the one we started with, except now we don't have a integration. I think it's a little bit dicier. So I want you all to try to write down the right trig substitution. Think about what we want x to be. We know it's not tangent. Is it going to be something times sine or something times secant? And also, what times sine? What times secant? So we want 25 minus x squared. We want the 25 to go away. We want this to equal 25 times our trig identity. Our trig identity is going to end up being 1 minus our trig function squared. Do we want that to be sine squared or secant squared? We want it to be sine squared. What would happen if we did secant squared? Sometimes people like James, that could work. I'm like, oh, almost. But the problem is, if you got 1 minus secant squared, 1 minus secant squared is actually a giant problem because 1 minus secant squared, well, secant squared minus 1 is equal to tangent squared. So 1 minus secant squared is equal to negative tangent squared. And you know what negative tangent squared always is? Negative. You know it's really not fun to take the square root of a negative number. So this really never works because the thing that would be inside the square root is always negative, and that's just not going to work out. So if you get 1 minus secant squared, go back and make the other choice. We want 1 minus sine squared. So what we really want is for x to be equal to 5 sine theta. So the x squared is 25 sine squared, and then 25 minus x squared is 25 minus 25 sine squared, which is 25 times 1 minus sine squared. So I always approach these problems thinking about what I want to happen, what trig identity I'm trying to look to make happen. So then I'm going to write this as the integral of the square root of 25 minus 5 sine theta squared. And this is where people make a mistake typically. They just write d theta. They let dx just magically turn into d theta without remembering that we actually have to find the derivative and say that dx is equal to the derivative of 5 sine theta times d theta. So really, really please, for me, make sure that when you do a trig substitution, you for sure find dx. It's going to be more than just d theta. It's going to be some trig function times d theta. It's typically going to be either cosine times d theta or secant theta, tangent theta times d theta, or the derivative tangent, which is secant squared theta times d theta. It's going to be one of those three things every time, with maybe a constant. So we're going to get 5 cosine theta d theta. And then we're going to start simplifying. This here becomes the square root of 25 times 1 minus sine squared. This is still 5 cosine theta. Theta. The square root of 25 is 5. The square root of cosine squared theta is cosine theta. So you end up with 5 times cosine times 5 times cosine, which is going to be 25 times the integral of cosine squared theta. Oh, we've got this cosine squared theta thing again. That's going to be 25 times 1/2 is 1 plus cosine of 2 theta. The reason I really want to talk about this one is because of what happens next. When we integrate this, we get theta plus sine of 2 theta divided by 2 plus c. And now we have to go back to x. What's theta equal to? Well, let's go back and look at our substitution. X equals 5 sine theta, then sine theta is equal to x divided by 5. And theta is equal to the arc sine of x divided by 5. Which is fine. What about sine of 2 theta? We can't just say it's going to be 2 times x over 5. And this is one that's really typically problematic. To deal with sine of 2 theta, the only way to deal with this is to use another trig identity, the double angle identity for sines. There's a lot of trig identities in this class. That's the way it is. There's a lot of trig identities to come up. So here, we're going to rewrite this as 25 over 2 times theta plus the double angle identity for sine is 2 sine theta times cosine theta. Those two's cancel. And now that we have sine and cosine of just the angle theta, we can do the same triangle thing we did before. We say, great, sine of theta is opposite of our hypotenuse. So sine of theta is x over 5. And the remaining third side is going to be the square root of 25 minus x squared. So that now we can write this as 25 over 2 times theta, which is the arc sine of x over 5, plus sine of theta, which is x over 5, times cosine of theta, which is the adjacent of our hypotenuse, which is the square root of 25 minus x squared over 5. Let's see. Pretty interesting. All right, I know we have 11 minutes left. Let's do a partial fractions problem or two, just so that you can have seen an example of that before I let you go. Partial fractions is another method of last resort. It's actually probably not as terrible as trig substitution, depending on your perspective. Partial fractions is really just an algebraic method of rewriting an integral to make it easier. So it's actually the algebra of simplifying it that's kind of the hard part. The integration is really not that. So let's look at a typical example. Let's say we want to find the integral of x plus 2 over x squared minus 9. Oh, no, that's fine. Yeah. So before you try partial fractions, you should look for a U substitution. Here, there's not a good choice, right? If I let u equal x squared minus 9, my du is 2x. If it was just x over x squared minus 9, u sub all the way. But since it's x plus 2, can't do it. Not going to work. Not a trig sub, because you really only use a trig sub if you have a square root or some like a square root or to the 3/2 power or the 5/2 power, a power where you have a half as the bottom part, like a 2 as your denominator. So you have a square root to a power. If you don't have a square root, you probably could do a trig sub here, but the plus 2 is dicey. Not a trig sub. This is definitely partial fraction, which I don't need to write again, but I am because. So partial fractions is a process of taking the integrand, x plus 2 over x squared minus 9. And to use partial fractions, 3 things have to be true. You have to have a rational function, meaning a polynomial divided by another polynomial. No square roots, no trig, exponential, other kinds of things, just positive integer powers of x over positive integer powers of x. The degree on top has to be strictly less than the degree on the bottom. And lastly, the denominator has to factor. Fact, that's what it doesn't say. Has to be a rational function. The degree of the top has to be strictly less than the degree on the bottom. And lastly, the denominator better factor. And you better factor it as much as possible. So in this case, the denominator factors as x minus 3 times x plus 3. And then what we're going to do is we're going to take that expression and try to write it as the sum of fractions with simpler denominators. I'm going to write this as something divided by x minus 3 plus something divided by x plus 3. And the somethings which we don't know, we're going to call a and b, typically. And the idea here is that you could multiply this first fraction by x plus 3 over x plus 3, and the second fraction by x minus 3 over x minus 3 to reconstitute the expression we have on the left-hand side, assuming that we have the right a and b value. So we don't actually do that, though. You could do it that way, but the easier thing to do is to take this expression, x plus 2 over x minus 3 times x plus 3. I should say this equation equal to a over x minus 3 plus b over x plus 3, and multiply both sides of this equation by the common denominator, which is x minus 3 times x plus 3. When you multiply this all the way to the thing on the left, denominators cancel, and we just end up with x plus 2. When you multiply it to the a over x minus 3, the x minus 3's cancel, and you're left with a times x plus 3. And similarly, when you multiply it by the b over x plus 3, the x plus 3's cancel, and you're left with b times x minus 3. When you do this, you shouldn't be left with any denominators. There's a couple ways of going about solving for a and b, but the thing I always recommend doing first, before you run out, is using what I call convenient values of x. There are values of x that'll make one of these factors 0. If I pick x equal to 3, on the left-hand side, I get 3 plus 2. On the right-hand side, I get a times 3 plus 3 plus b times 0. And b times 0 is 0. So I get 5 equal to 6 times a, or 5, 6 equal to a. Similarly, if I let x equal -3, I get -3 plus 2 on the left equal to a times 0 plus b times -3 minus 3. So -1 divided by -6 is equal to b. And then the whole idea is that we can now rewrite our integral. Instead of the integral of x plus 2 over x squared minus 9, we can write that as the integral of 5/6 over x minus 3 plus 1/6 over x plus 3. So we can rewrite this as the integral of a over x minus 3 plus b over x plus 3. Yes, sorry, thank you. And those are things that are not terrible to find the antiderivative at all. The antiderivative of 5/6 over x minus 3 is 5/6 times the natural log of the absolute value of x minus 3. And the antiderivative of 1/6 over x plus 3 is 1/6 times the natural log of the absolute value of x plus 3. The idea here is by making these things into the sum of simpler fractions, those simpler fractional expressions are then much easier to antidifferentiate. Yeah. So one more thing. So let's say we have the integral of x squared over x squared plus 1, which might technically not fall into the category of partial fractions. Okay. Why not? Because the denominator is, well, actually for 2 reasons. The degree on top is not smaller than the degree on the bottom, and the denominator doesn't actually factor. But ignoring the second thing I said, the degree on top being larger than or equal to the degree on the bottom means there's something else we can try. We can try doing polynomial division. We can think of this as x squared divided by x squared plus 1. X squared multiplied by 1 gives me x squared. So 1 times this is x squared plus 1. Subtract, that minus that is 0. And nothing minus 1 is -1. So we can rewrite this integral as the integral of the quotient 1 plus the remainder -1 over x squared plus 1. And now those are things we are able to antidifferentiate. The antiderivative of 1 is x. The antiderivative of -1 over x squared plus 1 is minus the arc tangent of x. But that actually speaks to a larger thing, which is that if you have something that's a rational function and the degree on top is greater than or equal to the degree on the bottom, typically doing polynomial division is the right first step. So if we were being assailed with the integral of, say, something like x cubed over x squared plus 2x minus 3, then before we could even think about partial fractions, we would need to do polynomial division. So we'd say, okay, great. X cubed divided by x squared plus 2x minus 3. I should write the other terms here, x squared, x cubed plus 0x squared plus 0x plus 0. And then you say x squared times x gives you x cubed. You multiply them all by x, you get x cubed plus 2x squared minus 3x. Subtract. That minus that's 0. 0x squared minus 2x squared is minus 2x squared. 0x minus 3x is plus 3x. 0. And you do it again. X squared times -2 gives me -2x squared. Negative times 2x is -4x. Negative times -3 is +6. Subtract. That minus that 0. 3x minus 4x is 7x. 0 minus 6 is -6. And then we can rewrite this integral as the integral of the quotient x minus 2 plus the remainder, 7x minus 6 over the denominator, x squared plus 2x minus 3. And then we can rewrite this as, we can anti-differentiate those parts and get x squared over 2 minus 2x plus the integral of 7x minus 6 over this denominator factors as x plus 3 times x minus 1. And then we can use partial fractions on this piece, which we will not do because it's 4:30. Have a lovely rest of your day. I imagine everyone has a second exam at some point in 21B. 17th.
I think ours is later.
Okay, I'll look. Okay. Is next Friday.
I think ours is week 8.
Okay. Okay.
Thank you.